still, because to examine the effect stress parameter is still in progress. So just to show a model for two-phase fluid in deformable porous media. First is the background. Yesterday, Bruno has talked about the model for one-phase fluid. He's imagining for the porous media with water, we can classify this regime to this phenomena to different regions by the saturation, such as from totally saturated to capillary regime, funicular, padular, and etc. Yesterday, we will focus on one-phase fluid, and for the polymer regime, basically a lot of researchers focus on that. They suppose using liquid bridge. For my research, will focus my interest on from the totally saturated to funicular. Obviously, the Grignard process. Before I start, let's make some basic assumption or preconditions. I want to make a model for the air system, or generally speaking, it's a non-wetting system. We assume it's a perfectly wetting solid phase, so which means the contact angle is 0, and we neglect currently we neglect the viscosity effects, and it's the current model is quasi-static regime. So the dynamic character for the two-phase fluid can be characterized by two parameters. The first one is the viscosity ratio, then capillary number. So my model will show from 5 o'clock to 7 o'clock this regime, and the third assumption that assume because we want to do a model for a deformable porous media. So but assume this deformation is very small. And then Pore network. The main function of Pore network that it can decompose the solid porous media by a network that we can generally to use the pore body and pore throat to represent the void space. We call the line space between the solid media is called pore body. The narrow part of the narrow neck we call the pore throat. So back to our model, we decompose the porous media with the regular triangulation technique Bruno has introduced yesterday. Here is two images about the network. The left image is generating with the regular triangulation. The right, if we use the solid phase, we can see the basic structure of this pore network. And if we go downscale, this is our basic pore unit. Left is the pore body. The void space between the tetrahedral shape is the pore body, and for the another terminology is the pore throat. We assume the section of the tetrahedral is the pore throat. It's no volume, but it's very important for the Grignard process. And the model of Grignard, the relationship between capillary pressure or metric suction can be the relation between capillary pressure, we call PC, and the pressure of two-phase, and the curvature can be described by the Laplace equation, as you know. And but for a very irregular geometry of the pore body, it's very hard to get a right curvature. So we turn to the numerical solution, which is follow the MSP method, in which we can solve the entry pressure by the force balance of the non-wetting interface. So with the right image is the geometry shape of the pore throat. We can solve that by this equation, get our entry capillary pressure for each pore body. So we get all the information, then we go to upscale to see our model. Really in the pore-scale network, they care about the void space, don't really care about the solid phase, but we care about both. So the left image is is our network. Usually okay, thank you. That works. Right. So the left image is our network. Usually in pair network models, they use a regular map to describe this. For clarify, I use the derivative to explain my model. So at the beginning, assume the porous media is initially totally saturated, which is in one side with connected with the non-wetting reservoir, another side connected with the wetting reservoir. All the pores are wetting pores. So we increase PC and the drainage starting from the top and keep increasing. For some pores, more and more pores being evaded, but for some pores may be disconnected with the wetting reservoir. So those is disconnected. In short term, we assume for this pores, the geometry is fixed, the volume is fixed, and the wetting pressure is constant in short terms. But in long terms, it can be drainaged. And at the end, even we increase the PC, those will be still there. So this is our model. And still in another consideration that is about boundary condition. Usually in experiment, they do experiment like we put some porous media in a container. We invade from one side, which means one side is non-wetting reservoir, another side is wet reservoir. So for the reservoir boundary condition is very clear. We can do that. But for the side boundaries, it's not very clear. You only do experiment in a container with rigid walls. So which means the pore route here is different from the pore route inside ones. So we should consider about that. I will talk about this effects later. So I implemented my model with our open source DM, open source software, DM, and let's do a very short test. This is generated with packing generated with YAD, and we do the drainage starting from one side, and then at the end, some pores disconnected with the non-wetting reservoir. We cut a slice from the 3 dimensions to make 2 dimensions. So this is our model, and because the disconnect events may happen in different time, which means we have different cluster of the trapped wetting phases. But at different time the wetting pressure is different, which means we have the local wetting pressure that's different. And we get a model. We want to verify it, so we compared with the experiment. His experiment results, but unfortunately we didn't get the original data from the experiment, so we compromised to do a repeating test. We do repeating, and got a lot of data, like the blue stars. Then we get averaged curve. This is a typical curve of the PCAW curve, and the dot is experiment date. It's not bad, but it's still at the gap. So we think about that. In my opinion, I think there are 2 reasons. In the experiment, they usually do experiment with column sample shape, which is long, very long, and the section is a cylinder. But for our case, so our model currently is restricted on the cuboid sample, but we can optimize it further. But currently, it's shaped like this. So this is the first reason, maybe. Another also space shape. Another thing is the boundary condition. That experiment usually focus on a subdomain of a very huge sample because it's take a long time, take a very long time to only focus on subdomain. But we don't know which subdomain of it, and so this is the second reason. Or if we generally speaking, maybe it's all about boundary condition and side effects. So let's dig deeper about the boundary condition side effects. As I said previously, that the wall, the pore route of the close to the boundary rigid wall is different from the inside ones. Well, the right image is the experiment image from our lab. We can see the drainage starting from the side pores. I'll show you my simulation results. Let's see. Okay, when you wait from one side, increasing PC, then you see a very huge displacement along the side boundary of its huge harness jump, and then starting really in parallel to the sample. But if we, okay, let's continue, and then keep increasing PC, at the end, the blue ones is the non-wetting phase, wet phase. The yellow is the wetting phase, also air. This is water. So even increase PC, such wetting phase is still disconnected with the wetting reservoir. Another case that if we think the boundary pores impermeable, which means it cannot be invaded, so the non-wetting phase will invade progressively with layer by layer. It's another situation that in experiment we hardly to see such phenomena. How many times do I have?
5 minutes at least.
At least, okay.
7 minutes.
7 minutes? Okay. I can skip this part, but I'll give you the conclusion that because I see that the difference between the experiment and our simulation, I think is a IRE problem. I've concluded that the IRE requirement for the two-phase fluid is more strictly than the dry pulse media. I think the IRE size for the two-phase fluid is larger than the dry pulse media. Okay, let's move forward. Let's focus on the geomechanics. So this is what I'm doing. This is the capillary force. So my focus on the solid pulse media. The fluid source applied on the solid particles basically is there are three types of them. First from non-wetting phase, another from wetting phase, and the third part is from the interface, non-wetting interface resuscitation. For the first two parts, it's very easy to calculate. We can do the integral on the curvature of the solid phase separately with wetting and non-wetting. But for this part, it's not that easy. Remember, we have solved the problem of the entry capillary pressure. So, which means the capillary pressure is not only working on the non-wetting phase, but also applied on the solid particles. Then we can use the results from the previous part to get this part. We can do the integrals along the non-wetting, wetting, solid contact lines. If we do the integral, we get the forces. Consider we have 6 particles here. It's okay. It belongs to 2 per unit. There is non-wetting. There is some water inside the 2 pores, and the force generated by the fluid can be like this. They will make the particle attract to each other. Apply to them. It's not what we do. If we do a simple test that we increase PC, starting region, but still totally saturated, keep increasing, starting weight. Okay, here's the air, here's the water. You can see, keep increasing, and there is a displacement of the interface. But for the particle here and particle here, they only involve one phase fluid. Currently, we think we negate the effects of viscosity. So for here, the total force for them is 0. The only forces involved here is the interface. And at the end. If we do a serious test on a very huge sample, we can see what happens. Here, we get generating a sample with our software, and then we do drainage from one side, but in odometric condition. Okay, what we can see, the blue line is a typical PCSW curve, but in rotate coordination. The y-axis is the saturation. The x-axis is the PC. And the red line is the macro parameters, you see, strain. Okay, starting region at the beginning, the sample is saturated, but you keep increasing. Okay, it's linear. It's expected, can be explained by the Tetragis effective principle stress, effective stress principle, and then can increase the sample starting region. Okay, then the strain new relations become nonlinear. Okay, it's called shrinking. And then keep increasing, because remember, assume that the deformation is very small, so the mechanical behavior for this sample is in elastic regime, which means after that it can be swelling. However, we think in short terms, some water may be trapped in this sample, and anyway, keep increase PC, but the effects cannot be eliminated. So the sample will not recover back to the initial state. We can see the string will stop here, but not swelling anymore. And if we dig deeper to see what happens in the macro scale, here we do experiment. Since they are in progress, that's why I changed my title, that we examine the Bishop effective stress parameters. Okay, the dash straight line is the chi equals SW curve, and the dash looks like straight lines with point is my estimation results. We get the chi by two ways, from a micro scale and micro scale. With two methods, they're closely also is expected because it's supposed to be the same in very good conditions. And but we can see it's all the chi is above this straight lines. So it's corresponding to the experiment by Bishop and Donald, which means the soil types is the marine and the silt. So I think we think a model can be suitable for those two kinds of soil. If we keep digging deeper, we see the macro, in macro scale, see what happens. Is the flow image about the macro stress and macro saturation. The y-axis is the height of the sample. We use the average technique to average the stress and stress in different level, in different height. We can see from those 4 images, we can get two information. First, from the red line, the saturation. You can see that the saturation changing progressively. In the beginning, here is the non-wetting reservoir, here is wetting reservoir. So it's expected that because just starting erosion, so here is with the low saturation, the high saturation is here. It's like the totally saturated. And the keeping PC, the distribution of the wetting phase is heterogeneous.
Yeah, you have to.
Okay, this is the last slide. Keep increasing. Okay, at the end, if we neglect the effects of boundary, we can see that it's okay. It's generally homogeneous. Another information is that we clearly see the relationship between macro stress and the saturation is related. So that's it. That's our results. And I have made some conclusions during the presentation. Okay, thank you for attention.
One question.
Thank you for your work. It's not so easy to solve the Laplace equation in 3 days, or maybe you don't solve exactly the Laplace equation, but to simulate the behavior of partially saturated porous medium. I ask myself, do you solve exactly your Laplace equation for complex geometry, for instance, for Quasi-static capillary bridge?
Yes. Yes. This is the geometry.
Okay, let me have a look.
MSP theory.
How do you compute exactly the tensile force and the capillary force for Quasi-static bridge, for instance, between the 3 grains?
Between what? Between the...
How do you compute the capillary forces, the whole capillary forces?
Yeah.
You need the tensile force contribution and the...
it's very, I think it's very... I think it's a very long story. First part we get the let's see the entry postulate radius. Then according to Young's substitution, we can get the PC. Then we do the integrals. Basically, it's in 3 dimensions. We can we can use the tools to solve this problem. But it's a very long story. We have some people on that. If you're very interested, you can discuss later. But for the geometry, it's basically should be like this. We can not exactly the solution, but we solve this numerically. So, but with the
okay. In fact, I don't understand very well. But anyway, we will discuss as a coffee break.
Okay.
Have you read the PhD thesis from Jean-Philippe Graff from Montpellier, LMGC?
I'm sorry.
They've got interesting experiments on quasi-static capillary bridges. And they are
capillary bridges.
Drying process, for instance, the sudden decrease of the capillary force just before the coalescence, or after the coalescence and before, when the whole capillary bridge splits into three separate capillary bridges. Can you observe this? I think it's an important point for you here.
And I saw to put some from the the focus from here to here. For the you said Capillary model, it's not my interest. It's not about by another member of the group.
Okay.
But we have this kind of model. We can we can do that. We have this kind of model in yet. Any question?
Thank you very much, and we change.